Hello and welcome to our presentation on SciTuner, a selective data acquisition framework for accurate and fair machine learning models. I'm Hyun-tae from the Data Intelligence Lab at KAIST. Responsible AI is extremely important, and especially for companies like Google, IBM, and Microsoft, they really deploy AI to the world. So just to summarize these codes, Google is saying that AI has significant potential to help solve challenging problems, but it's also critical that AI is used and developed responsibly. IBM also says that performance is very important, but you also need to build, evaluate, and monitor for trust. Lastly, Microsoft mentions that AI systems are developed responsibly and in ways that warrant people's trust. So in our work, we focus on model fairness among the key issues in responsible AI that also contain robustness, explainability, and so on. So fairness is about not discriminating. And you have probably heard a lot about fairness nowadays because as machine learning becomes prevalent, fairness becomes a critical issue. Recently, there is a famous article written by ProPublica that talks about the Compass software. This is a tool that predicts a defendant's risk of committing another crime, and it is called the recidivism risk. The problem is that Compass overestimates Black people's recidivism risk compared to white people more than reality. And the reason is that the data that trains Compass is very biased to Black people committing crime. So, as in the Compass example, the training data could be the root cause of unfairness, because machine learning model is only as good as its data. Therefore, we can acquire new data to improve both model fairness and accuracy. There are many tools available for acquiring data, including dataset discovery tools, crowdsourcing, and even simulator-based data generation. Note that our problem is not the same as active learning, which is labeling existing data, and this is a problem of finding new data from outside. Okay, so we want to acquire data to improve both accuracy and fairness. But blindly acquiring data is not the right approach. Let's look at this example. We have 5 different country slices of customers, such as America, Europe, APAC, and others. And the height of the white box means the number of training data. In this case, we already have a lot of America data, so we probably don't need additional America data to train the model, and it can even make the model be biased to America data. We instead want to acquire data for the other slices that don't have enough data like Africa. So now we want to acquire possibly different amounts of data per slice. So the goal of this work is to minimize not only the total model loss, but also the unfairness in losses. This notion of fairness is a little different from the traditional fairness notion like disparate impact. This is saying that for different slices, I want to provide the same loss, which means that if a company is providing some service worldwide, we want to provide the same quality service to all customers, which is an extremely important measure for a company. So how do we achieve the goal? Well, a water filling strategy that acquires data such that all slices have equal amounts of data in the end is a good starting point as in the bottom left figure, but it's not optimal. That's because some slices may need more data to obtain the same model loss as other slices because the data is just different. For example, on the bottom right, you may need to acquire more data for APAC customers compared to other countries in order to have a better loss and unfairness. So, how do we do that well? In our work, we exploit learning curves of the model. Here, the learning curve can be used to estimate the model loss on a slice, given more labeled data. Many recent works observe that if we acquire more data, the loss of a model goes down in a power law function. The below figure shows the learning curves of the UTK-based data set we used in our experiments. The x-axis is the number of training examples, and the y-axis is the estimated model loss. Our key observation here is that as the size of the slice increases, the loss decreases and has a power law curve. And I'm showing you the learning curves for 2 slices, one for white male face images and another for Black female face images. We can see that different slices may have different learning curves, and that's why we need to acquire different amounts of data per slice. So from the learning curves, we can determine how much data to acquire per slice to build the optimal model. So for now, let's assume that the learning curves are perfectly reliable, although they are not actually perfect. And I'm going to talk about how to cope with unreliable learning curves later. So our objective is to determine the number of examples to acquire per slice to minimize total model loss and unfairness. So in the formula, the first part is minimizing the total loss of slices based on our learning curve-based estimation. And the second term penalizes underperforming slices. So if a slice has a higher loss than average, we give some penalty to acquire more data on that slice. Since minimizing loss and unfairness are not always aligned, we introduce a lambda term to balance between minimizing each of them. And this is subject to the total acquisition cost being within some budget B. And we use an acquisition cost function that returns a different value for different slices because the cost for acquiring the same amounts of data can be different depending on the slice. For example, it may be much easier to acquire America data than APAC or other regions data. This optimization problem is convex, so it can be easily optimized with any off-the-shelf servers. So this is an architecture of slice tuner. So from the learning curve estimation, slice tuner can perform selective data acquisition on given slices in order to optimize both model loss and unfairness. We assume that the runtime bottleneck to build a machine learning model is the time to actually acquire data. Since many recent works show that obtaining high-quality data is very expensive, our framework aims to optimize the number of examples before actual acquisition. We now explain two important technical challenges we address. One is on the data management aspect, where we need to efficiently feed learning curves. So to feed a learning curve, we first assume that there's enough validation data for each slice to draw learning curves. We believe that this is a common scenario for many companies where we have some data and want to acquire more to improve the existing model. Then the learning curve can be constructed by training models on subsets of data and computing losses on the validation set. Specifically, we train the models on a random subset of data with different sizes and use weighted nonlinear least squares estimation to feed a curve, assuming a power law. However, learning curve fitting for all slices independently is very expensive. So our solution is to amortize computation by training one model on X% subsets of all slices. Instead of taking an X% subset of one slice and leaving the rest as is to train each model, we take X% subsets of all slices and train a model. This approach assumes that taking subsets of other slices does not affect the model accuracy on the current slice. But in reality, this independence assumption does not hold, and it will make the learning curves more unreliable. So we are going to explain how to handle the dependency between slices in the next slide. And more detailed implementations and other possible optimizations are provided in our paper. So the remaining challenge is handling unreliable learning curves. Indeed, there are more issues of learning curve unreliability. If the slices are too small, then the curves are not accurate because we don't have enough data to fit a curve. And even worse, acquiring data for one slice may influence other slices. Here, the left graph from the UTK phase dataset experiment is showing how influence happens. The x-axis is the number of training examples of the white male slice, and the y-axis is the loss of all the slices. So as you acquire training data for white male slice only, you can see a decrease in the loss for that slice as shown in blue color. But for most of the other slices, the losses go up, which means acquiring only white male data has a negative influence on those slices. But for the white female slice, which has an orange color, the loss decreases as well. That's because the white female slice shares common features with the white male slice, which is white skin color. So it actually benefits from the acquisition. So the direction of influence can go both ways, positive and negative. But the important thing is that there is a magnitude of influence. Let me explain more about the influence using the example on the bottom right. Suppose we have 3 slices that have different shapes, circles, squares, and triangles. And the line represents the decision boundary of the model. So if we acquire the data for the triangles only, it may introduce some bias and shift the decision boundary to the left. So it's going to change the losses of other slices and therefore their learning curves as well. So our solution is to iteratively update curves as more data is acquired. But the next question is, how often should we do this? So there are 2 competing objectives. So each iteration is expensive and involves model training on subsets and curve fitting as discussed before. On the other hand, we do not want to use inaccurate learning curves. So there must be some sweet spot in between. So our algorithm can be summarized as follows. First, we ensure a minimum slice size to draw learning curves. It doesn't have to be accurate, and tens of examples is enough to draw learning curves for our experiments. Then, we acquire data as long as the estimated influence is not too large. Then, we refit the learning curves and repeat this procedure until we run out of budget. So the key question is, how do we estimate the influence? It is extremely difficult to model the influence analytically. So we use a proxy, which we call imbalance ratio change. The imbalance ratio captures the bias of the data and is defined to be the largest slice size divided by the smallest slice size. Our intuition is that if the imbalance ratio changes a lot, there is some influence going on. Let's go back to our toy example. If you acquire only red triangles, as in the top right figure, this is adding more bias toward the triangle slice, and the imbalance ratio increases from 1 to 2. So this is an indication that influence causes the decision boundary to shift. On the other hand, if we increase the slice sizes with the same proportion as in the bottom right figure, so if we add 1 triangle, 1 circle, and 1 square, the bias doesn't change, and the decision boundary tends to shift much less compared to the previous case. And the imbalance ratio doesn't change as well. Let me explain our iterative update algorithm with an example. Here, we have the following slice sizes per each country, and the total budget is 400. We also assume the cost function for all slices always returns 1, but I will explain later how we can define a cost function in the real use case. So firstly, we initialize the imbalance ratio change limit t to 1, and the imbalance ratio is 300 over 100, which is 3. Then we solve the convex optimization problem using the entire remaining budget and check whether the resulting imbalance ratio change exists t or not. Here, the resulting amounts of data to acquire per slice are in the bottom figure, and the imbalance ratio changes from 3 to 1. So the imbalance ratio change becomes 2, which is larger than limit t. So if the imbalance ratio change exists t, we think that there may be some influence between slices. And we'll limit the number of examples acquired so that the resulting imbalance ratio change does not exceed t. And then we refit the curves. So the second line shows the original solution when using the entire remaining budget. And we can easily compute ratio so that the imbalance ratio change does not exceed t. In this example, the ratio is 0.25, and the third line is the actual output. Then we increase t by 1. And there are other strategies to adjust the limit t in our paper, which determines how often should we update the curves. Then we repeat this procedure until we run out of the entire budget. From now on, I'm going to show our experimental results on real data sets and explain the details one by one. In this talk, I will only show the results for 2 data sets, Fashion MNIST and UTK face. For the Fashion MNIST dataset, we used the 10 slices for 10 classes, which consists of shoes, shirts, and more. And for the UTK face dataset, we used 8 slices combining 2 genders and 4 races. For the data acquisition, we use 2 different settings. For fashionist, we first simulate data acquisition by starting from a subset and adding more existing examples. So we can define the cost function to always return 1. But for the UTK face data set, we use a real scenario where we crowdsource new face images from the world using Amazon Mechanical Turk. So we pay workers and they actually acquire some images from any website. So the acquisition cost per slice is proportional to the average time for a worker to find an image for that slice. And you can imagine this time is different depending on the slice. So for the white male slice, it takes an average of 82 seconds to find an image. Whereas for the last one, which is for the Indian female slice, it takes 104 seconds and thus much longer. So we can set the acquisition function to give a cost that is proportional to the search time. So now we move on to the experiments. First, we compare slice tuner with 2 baselines. One is uniform, where we acquire the same amounts of data per slice, and the other one is water filling, which is what I described before. For a more detailed comparison, we consider 3 data scenarios. One is just basic, one is bad for a uniform baseline, and one is bad for a water filling baseline. The details are not too important, and the point here is that we want to consider many different scenarios for an extensive evaluation. The results here show that slice tuner outperforms both baseline in terms of model loss and unfairness. The left graph shows the loss results. The blue plot is when you do not acquire the data, and the green and orange bars are the uniform and water filling baseline respectively. And the red bar is a slice tuner. So you can see that slice tuner has better losses than others. Now on the right-hand side, you can see the unfairness results, where lower value is better, and we use a measure called average equalized error rate, which is basically the unfairness I was talking about. And you can see a much more drastic improvement for slice tuner, because we explicitly optimize on unfairness. The result for UTK face data shows similar trends, although the loss improvement is less drastic than that of the fashion amnesty dataset. But what if the learning curves are unreliable? In this experiment, we lower the initial slice sizes to tens of examples. On the top right, you can see that the learning curves are noisy and so unreliable. So in this case, we compare slice tuner with 2 baselines using different budgets, which correspond different bars in the figures. But if you look at the result, slice tuner still outperforms the 2 baselines. And the reason is that slice tuner can exploit the relative differences of learning curves in terms of loss and steepness. So even if individually the learning curve is not reliable, it's the difference that matters. And as long as that information is available, slice tuner exploits that difference. And in the worst case, where learning curves are totally random, slice tuner just defer back to the performance of one of the baselines, which is not really a bad option either. However, as more data is acquired, we expect that the learning curves will gradually become more reliable and informative by our iterative update algorithm. Lastly, we evaluate our efficient learning curve generation method. If you look at the runtime of a naive approach that exhaustively generates learning curves in the bottom table, slice tuner is an order of magnitude faster and therefore practically efficient. And it obtains slightly worse or even better loss and unfairness results. In the case where slice tuner has a better loss, we suspect that optimization of taking X% examples of all slices together has the effect of removing bias among the slices. So to conclude the talk, we propose slice tuner, a selective data acquisition framework that uses learning curves to determine how much data should be acquired per slice to optimize both loss and unfairness. Moreover, the proposed algorithm iteratively generates learning curves efficiently and reliably. We demonstrated on real data sets that slice tuner outperforms the baseline in terms of model loss and unfairness, even with small data. So we believe that slice tuner is a practical data acquisition tool for fair and accurate models. Thank you for listening to our talk.